Hello everyone, how's it going? Let me get this up really quick. I will be taking questions, especially after we finish this audiobook, which we only have an hour left. Only an hour. So let's finish that right now. After we finish. Okay, here we go. We got it all up.
Chapter 9. The Arrow of Time. In previous chapters, we have seen how our views of the nature of time have changed over the years. Up to the beginning of this century, people believed in an absolute time. That is, each event could be labeled by a number called time in a unique way, and all good clocks would agree on the time interval between two events. However, the discovery that the speed of light appeared the same to every observer, no matter how he was moving, led to the theory of relativity. And in that one had to abandon the idea that there was a unique absolute time. Instead, each observer would have his own measure of time as recorded by a clock that he carried. Clocks carried by different observers would not necessarily agree. Thus, time became a more personal concept relative to the observer who measured it. When one tried to unify gravity with quantum mechanics, one had to introduce the idea of imaginary time. Imaginary time is indistinguishable from directions in space. If one can go north, one can turn around and head south equally. If one can go forward in imaginary time, one ought to be able to turn around and go backward. This means that there can be no important differences between the forward and backward directions of imaginary time. On the other hand, when one looks at real time, there's a very big difference between the forward and backward directions, as we all know. Where does this difference between the past and the future come from? Why do we remember the past, but not the future? The laws of science do not distinguish between the past and the future. More precisely, as explained earlier, the laws of science are unchanged under the combination of operations, or symmetries, known as CP and T. C means changing particles for antiparticles. P means taking the mirror image, so left and right are interchanged. And T means reversing the direction of motion of all particles, in effect, running the motion backward. The laws of science that govern the behavior of matter under all normal situations are unchanged under the combination of the two operations, C and P, on their own. In other words, life would be just the same for the inhabitants of another planet who were both mirror images of us and who were made of antimatter rather than matter. If the laws of science are unchanged by the combination of operations C and P, and also by the combination CP and T, they must also be unchanged under the operation T alone. Yet there's a big difference between the forward and backward directions of real time and ordinary life. Imagine a cup of water falling off a table and breaking into pieces on the floor. If you take a film of this, you can easily tell whether it's being run forward or backward. If you run it backward, you see the pieces suddenly gather themselves together off the floor, jump back to form a whole cup on the table. You can tell that the film is being run backward because this kind of behavior is never observed in ordinary life. If it were, crockery manufacturers would go out of business. The explanation that is usually given as to why we don't see broken cups gathering themselves together off the floor and jumping back onto the table is that it is forbidden by the second law of thermodynamics. This says that in any closed system disorder, or entropy, always increases with time. In other words, it is a form of Murphy's Law. Things always tend to go wrong. An intact cup on the table is a state of high order, but a broken cup on the floor is a disordered state. One can go readily from the cup on the table in the past to the broken cup on the floor in the future, but not the other way round. The increase of disorder, or entropy, with time is one example of what is called an arrow of time, something that distinguishes the past from the future, giving a direction to time. There are at least 3 different arrows of time. First, there is the thermodynamic arrow of time, the direction of time in which disorder or entropy increases. Then there is the psychological arrow of time. This is the direction in which we feel time passes, the direction in which we remember the past, but not the future. Finally, there's the cosmological arrow of time. This is the direction of time in which the universe is expanding rather than contracting. In this chapter, I shall argue that the no-boundary condition for the universe, together with the weak anthropic principle, can explain why all three arrows point in the same direction, and moreover, why a well-defined arrow of time should exist at all. I shall argue that the psychological arrow is determined by the thermodynamic arrow, and that these two arrows necessarily always point in the same direction. If one assumes the no-boundary condition for the universe, we shall see that there must be well-defined thermodynamic and cosmological arrows of time, but they will not point in the same direction for the whole history of the universe. However, I shall argue that it is only when they do point in the same direction that conditions are suitable for the development of intelligent beings who can ask the question, why does disorder increase in the same direction of time as that in which the universe expands? I shall discuss first the thermodynamic arrow of time. The second law of thermodynamics results from the fact that there are always many more disordered states than there are ordered ones. For example, consider the pieces of a jigsaw in a box. There is one, and only one, arrangement in which the pieces make a complete picture. On the other hand, there are a very large number of arrangements in which the pieces are disordered and don't make a picture. Suppose a system starts out in one of the small number of ordered states. As time goes by, the system will evolve according to the laws of science, and its state will change. At a later time, it is more probable that the system will be in a disordered state than in an ordered one, because there are more disordered states. Thus, disorder will tend to increase with time if the system obeys an initial condition of high order. Suppose the pieces of the jigsaw start off in a box in the ordered arrangement in which they were forming a picture. If you shake the box, the pieces will take up another arrangement. This will probably be a disordered arrangement in which the pieces don't form a proper picture, simply because there are so many more disordered arrangements. Some groups of pieces may still form parts of the picture, but the more you shake the box, the more likely it is that these groups will get broken up and the pieces will be in a completely jumbled state in which they don't form any sort of picture. So the disorder of the pieces will probably increase with time if the pieces obey the initial condition that they start off in a condition of high order. Suppose, however, that God decided that the universe should finish up in a state of high order, but that it didn't matter what state it started in. At early times, the universe would probably be in a disordered state. This would mean that disorder would decrease with time. You would see broken cups gathering themselves together and jumping back onto the table. However, any human beings who were observing the cups would be living in a universe in which disorder decreased with time. Now, I shall argue that such beings would have a psychological arrow of time that was backward. That is, they would remember events in the future and not remember events in the past. When the cup was broken, they would remember it being on the table, but when it was on the table, they would not remember it being on the floor. It's rather difficult to talk about human memory because we don't know how the brain works in detail. We do, however, know all about how computer memories work. I shall therefore discuss the psychological arrow of time for computers. I think it's reasonable to assume that the arrow for computers is the same as that for humans. If it were not, one could make a killing on the stock exchange by having a computer that would remember tomorrow's prices. A computer memory is basically a device containing elements that can exist in either of two states. A simple example is an abacus. In its simplest form, this consists of a number of wires. On each wire is a bead that can be put in one of two positions. Before an item is recorded in a computer's memory, the memory is in a disordered state, with equal probabilities for the two possible states. The abacus beads are scattered randomly on the wires of the abacus. After the memory interacts with the system to be remembered, it will definitely be in one state or the other according to the state of the system. Each abacus bead will be at either the left or the right of the abacus wire. So, the memory has passed from a disordered state to an ordered one. However, in order to make sure that the memory is in the right state, it is necessary to use a certain amount of energy to move the bead or to power the computer, for example. This energy is dissipated as heat and increases the amount of disorder in the universe. One can show that this increase in disorder is always greater than the increase in the order of the memory itself. Thus, the heat expelled by the computer's cooling fans means that when a computer records an item in memory, the total amount of disorder in the universe still goes up. The direction of time in which a computer remembers the past is the same as that in which disorder increases. Our subjective sense of the direction of time, the psychological arrow of time, is therefore determined within our brain by the thermodynamic arrow of time. Just as a computer, we must remember things in the order in which entropy increases. This makes the second law of thermodynamics almost trivial. Disorder increases with time because we measure time in the direction in which disorder increases. You can't have a safer bet than that. But why should the thermodynamic arrow of time exist at all? Or in other words, why should the universe be in a state of high order at one end of time, the end that we call the past? Why is it not in a state of complete disorder at all times? After all, this might seem more probable. And why is the direction of time in which disorder increases the same as that in which the universe expands? In the classical theory of general relativity, one cannot predict how the universe would have begun, because all the known laws of science would have broken down at the Big Bang singularity. The universe could have started out in a very smooth and ordered state. This would have led to well-defined thermodynamic and cosmological arrows of time, as we observe. But it could equally well have started out in a very lumpy and disordered state. In that case, the universe would already be in a state of complete disorder, so disorder could not increase with time. It would either stay constant, in which case there would be no well-defined thermodynamic arrow of time, or it would decrease, in which case the thermodynamic arrow of time would point in the opposite direction of the cosmological arrow. Neither of these possibilities agrees with what we observe. However, as we've seen, classical general relativity predicts its own downfall. When the curvature of space-time becomes large, quantum gravitational effects will become important, and the classical theory will cease to be a good description of the universe. One has to use a quantum theory of gravity to understand how the universe began. In a quantum theory of gravity, as we saw in the last chapter, in order to specify the state of the universe, one would still have to say how the possible histories of the universe would behave at the boundary of space-time in the past. One could avoid this difficulty of having to describe what we do not and cannot know only if the histories satisfy the no-boundary condition. They are finite in extent, but have no boundaries, edges, or singularities. In that case, the beginning of time would be a regular, smooth point of space-time, and the universe would have begun its expansion in a very smooth and ordered state. It could not have been completely uniform because that would violate the uncertainty principle of quantum theory. There had to be small fluctuations in the density and velocities of particles. The no-boundary condition, however, implied that these fluctuations were as small as they could be, consistent with the uncertainty principle. The universe would have started off with a period of exponential or inflationary expansion in which it would have increased its size by a very large factor. During this expansion, the density fluctuations would have remained small at first, but later would have started to grow. Regions in which the density was slightly higher than average would have had their expansion slowed down by the gravitational attraction of the extra mass. Eventually, such regions would stop expanding and collapse to form galaxies, stars, and beings like us. The universe would have started in a smooth and ordered state and would have become lumpy and disordered as time went on. This would explain the existence of the thermodynamic arrow of time. But what would happen if and when the universe stopped expanding and began to contract? Would the thermodynamic arrow reverse and disorder begin to decrease with time? This would lead to all sorts of science fiction-like possibilities for people who survive from the expanding to the contracting phase. Would they see broken cups gathering themselves together off the floor and jumping back onto the table? Would they be able to remember tomorrow's prices and make a fortune on the stock market? It might seem a bit academic to worry about what would happen when the universe collapses again, as it will not start to contract for at least another 10,000 million years. But there is a quicker way to find out what will happen. Jump into a black hole. The collapse of a star to form a black hole is rather like the later stages of the collapse of the whole universe. So if disorder were to decrease in the contracting phase of the universe, one might also expect it to decrease inside a black hole. So perhaps an astronaut who fell into a black hole would be able to make money at roulette by remembering where the ball went before he placed his bet. Unfortunately, however, he would not have long to play before he was turned into spaghetti. Nor would he be able to let us know about the reversal of the thermodynamic arrow, or even bank his winnings, because he'd be trapped behind the event horizon of the black hole. At first, I believed that disorder would decrease when the universe recollapsed. This was because I thought that the universe had to return to a smooth and ordered state when it became small again. This would mean that the contracting phase would be like the time reverse of the expanding phase. People in the contracting phase would live their lives backward. They'd die before they were born and get younger as the universe contracted. This idea is attractive because it would mean a nice symmetry between the expanding and contracting phases. However, one cannot adopt it on its own, independent of other ideas about the universe. The question is it implied by the no-boundary condition, or is it inconsistent with that condition? As I said, I thought at first that the no-boundary condition did indeed imply that disorder would decrease in the contracting phase. I was misled partly by the analogy with the surface of the Earth. If one took the beginning of the universe to correspond to the North Pole, then the end of the universe should be similar to the beginning, just as the South Pole is similar to the North. However, the North and South Poles correspond to the beginning and end of the universe in imaginary time. The beginning and end in real time can be very different from each other. I was also misled by work I'd done on a simple model of the universe in which the collapsing phase looked like the time reverse of the expanding phase. However, a colleague of mine, Don Page of Penn State University, pointed out that the no-boundary condition did not require the contracting phase necessarily to be the time reverse of the expanding phase. Further, one of my students, Raymond Laflamme, found that in a slightly more complicated model, the collapse of the universe was very different from the expansion. I realized that I'd made a mistake. The no-boundary condition implied that disorder would in fact continue to increase during the contraction. The thermodynamic and psychological arrows of time would not reverse when the universe begins to recontract or inside black holes. What should you do when you find you've made a mistake like that? Some people never admit that they are wrong and continue to find new and often mutually inconsistent arguments to support their case, as Eddington did in opposing black hole theory. Others claim to have never really supported the incorrect view in the first place, or if they did, it was only to show that it was inconsistent. It seems to me much better and less confusing if you admit in print that you were wrong. A good example of this was Einstein, who called the cosmological constant, which he introduced when he was trying to make a static model of the universe, the biggest mistake of his life. To return to the arrow of time, there remains the question, why do we observe that the thermodynamic and cosmological arrows point in the same direction? Or in other words, why does disorder increase in the same direction of time as that in which the universe expands? If one believes that the universe will expand and then contract again, as the no-boundary proposal seems to imply, this becomes a question of why we should be in the expanding phase rather than the contracting phase. One can answer this on the basis of the weak anthropic principle. Conditions in the contracting phase would not be suitable for the existence of intelligent beings who could ask the question, why is disorder increasing in the same direction of time as that in which the universe is expanding? The inflation in the early stages of the universe, which the no-boundary proposal predicts, means that the universe must be expanding at very close to the critical rate at which it would just avoid recollapse, and so will not recollapse for a very long time. By then, all the stars will have burned out, and the protons and neutrons in them will probably have decayed into light particles and radiation. The universe will be in a state of almost complete disorder. there will be no strong thermodynamic arrow of time. Disorder couldn't increase much because the universe would be in a state of almost complete disorder already. However, a strong thermodynamic arrow is necessary for intelligent life to operate. In order to survive, human beings have to consume food, which is an ordered form of energy, and convert it into heat, which is a disordered form of energy. Thus, intelligent life could not exist in the contracting phase of the universe. This is the explanation of why we observe that the thermodynamic and cosmological arrows of time point in the same direction. It is not that the expansion of the universe causes disorder to increase. Rather, it is that the no-boundary condition causes disorder to increase and the conditions to be suitable for intelligent life only in the expanding phase. To summarize, the laws of science do not distinguish between the forward and backward directions of time. However, there are at least 3 arrows of time that do distinguish the past from the future.
Oh my
They're
goodness.
the thermodynamic arrow, the direction of time in which disorder increases, the psychological arrow, the direction of time in which we remember the past and not the future, and the cosmological arrow, the direction of time in which the universe expands rather than contracts. I've shown that the psychological arrow is essentially the same as the thermodynamic arrow, so that the two would always point in the same direction. The no-boundary proposal for the universe predicts the existence of a well-defined thermodynamic arrow of time, because the universe must start off in a smooth and ordered state. And the reason we observe this thermodynamic arrow to agree with the cosmological arrow is that intelligent beings can exist only in the expanding phase. The contracting phase will be unsuitable because it has no strong thermodynamic arrow of time. The progress of the human race in understanding the universe has established a small corner of order in an increasingly disordered universe. If you remember every word in this book, your memory will have recorded about 2 million pieces of information. The order in your brain will have increased by about 2 million units. However, while you have been reading the book, you will have converted at least 1,000 calories of ordered energy in the form of food into disordered energy in the form of heat that you lose to the air around you by convection and sweat. This will increase the disorder of the universe by about 20 million units, or about 10 million times the increase in order in your brain. And that's if you remember everything in this book. In the next chapter, I'll try to increase the order in our neck of the woods a little further by explaining how people are trying to fit together the partial theories that I've described to form a complete unified theory that would cover everything in the universe. Chapter 10. The Unification of Physics. As was explained in the first chapter, it would be very difficult to construct a complete unified theory of everything in the universe all at one go, so instead, we've made progress by finding partial theories that describe a limited range of happenings and by neglecting other effects of or approximating them by certain numbers. Chemistry, for example, allows us to calculate the interactions of atoms without knowing the internal structure of an atom's nucleus. Ultimately, however, one would hope to find a complete, consistent, unified theory that would include all these partial theories as approximations, and that did not need to be adjusted to fit the facts by picking the values of certain arbitrary numbers in the theory. The quest for such a theory is known as the unification of physics. Einstein spent most of his later years unsuccessfully searching for a unified theory, but the time wasn't ripe. There were partial theories for gravity and the electromagnetic force, but very little was known about the nuclear forces. Moreover, Einstein refused to believe in the reality of quantum mechanics, despite the important role he'd played in its development. Yet it seems that the uncertainty principle is a fundamental feature of the universe we live in. A successful unified theory must therefore necessarily incorporate this principle. As I shall describe, the prospects for finding such a theory seem to be much better now because we know so much more about the universe. But we must beware of overconfidence. We have had false dawns before, At the beginning of the century, for example, it was thought that everything could be explained in terms of the properties of continuous matter, such as elasticity and heat conduction. The discovery of atomic structure and the uncertainty principle put an emphatic end to that. Then again, in 1928, physicist and Nobel Prize winner Max Born taught a group of visitors to Göttingen University, "Physics as we know it will be over in 6 months." His confidence was based on the recent discovery by Dirac of the equation that governed the electron. It was thought that a similar equation would govern the proton, which was the only other particle known at the time, and that would be the end of theoretical physics. However, the discovery of the neutron and of nuclear forces knocked that one on the head too. Having said this, I still believe there are grounds for cautious optimism that we may now be near the end of the search for the ultimate laws of nature. In previous chapters, I've described general relativity, the partial theory of gravity, and the partial theories that govern the weak, the strong, and the electromagnetic forces. The last three may be combined in so-called grand unified theories, or GUTS, which are not very satisfactory because they do not include gravity and because they contain a number of quantities, like the relative masses of different particles, that cannot be predicted from the theory, but have to be chosen to fit observations. The main difficulty in finding a theory that unifies gravity with the forces is that general relativity is a classical theory. That is, it does not incorporate the uncertainty principle of quantum mechanics. On the other hand, the other partial theories depend on quantum mechanics in an essential way. A necessary first step, therefore, is to combine general relativity with the uncertainty principle. As we've seen, this can produce some remarkable consequences, such as black holes not being black, and the universe not having any singularities, but being completely self-contained and without a boundary. The trouble is, as explained in Chapter 7, the uncertainty principle means that even empty space is filled with pairs of virtual particles and antiparticles. These pairs would have an infinite amount of energy, and therefore, by Einstein's famous equation, E equals mc squared, they would have an infinite amount of mass. Their gravitational attraction would thus curve up the universe to infinitely small size. Rather similar, seemingly absurd infinites occur in the other partial theories, but in all these cases, the infinites can be cancelled out by a process called renormalization. This involves cancelling the infinities by introducing other infinities. Although the technique is rather dubious mathematically, it does seem to work in practice, and has been used with these theories to make predictions that agree with observations to an extraordinary degree of accuracy. Renormalization, however, does have a serious drawback from the point of view of trying to find a complete theory, because it means that the actual values of the masses and the strength of the forces cannot be predicted from the theory, but have to be chosen to fit the observations. In attempting to incorporate the uncertainty principle into general relativity, one has only two quantities that can be adjusted: the strength of gravity and the value of the cosmological constant. But adjusting these is not sufficient to remove all the infinites. One theory has a theory that seems to predict that certain quantities, such as the curvature of space-time, are all really infinite. Yet these quantities can be observed and measured to be perfectly finite. This problem is combining general relativity and the uncertainty principle have been suspected for some time, but was finally confirmed by detailed calculations in 1972. 4 years later, a possible solution called supergravity was suggested. The idea was to combine the spin-2 particle called the graviton, which carries the gravitational force, with certain other new particles of spin, 3-2, 1, 1-2, and 0. In a sense, all these particles could then be regarded as different aspects of the same superparticle, thus unifying the matter particles with spin 1-2 and 3-2 with the force-carrying particles of spin 0, 1, and 2. The virtual particle-antiparticle pairs of spin 1-2 and 3-2 would have negative energy, and so would tend to cancel out the positive energy of the spin 2, 1, and 0 virtual pairs. This would cause many of the possible infinities to cancel out, but as was suspected, some infinities might still remain. However, the calculations required to find out whether or not there were any infinities left uncancelled, were so long and difficult that no one was prepared to undertake them. Even with a computer, it was reckoned it would take at least 4 years, and the chances were very high that one would make at least one mistake, probably more. So one would know one had the right answer only if someone else repeated the calculation and got the same answer, and that didn't seem very likely. Despite these problems, and the fact that the particles in the supergravity theories did not seem to match the observed particles, most scientists believe that supergravity was probably the right answer to the problem of the unification of physics. It seemed the best way of unifying gravity with the other forces, though. However, in 1984, there was a remarkable change of opinion in favor of what are called string theories. In these theories, the basic objects are not particles, which occupy a single point of space, but things that have a length but no other dimension, like an infinitely thin piece of string. These strings may have ends, the so-called open strings, or they may be joined up with themselves in closed loops, closed strings. A particle occupies one point of space at each instant of time. Thus, its history can be represented by a line in space-time, the world line. A string, on the other hand, occupies a line in space at each moment of time, so its history in space-time is a two-dimensional surface called the world sheet. Any point on such a world sheet can be described by two numbers, one specifying the time and the other the position of the point on the string. The world sheet of an open string is a strip. Its edges represent the paths through space-time at the ends of the string. The world sheet of a closed string is a cylinder or tube. A slice through the tube is a circle, which represents the position of the string at one particular time. Two pieces of string can join together to form a single string. In the case of open strings, they simply join at the ends, which, while in the case of closed strings, it's like the two legs joining on a pair of trousers. Similarly, a single piece of string can divide into two strings. In string theories, what were previously thought of as particles are now pictured as waves traveling down the string, like waves on a vibrating kite string. The emission or absorption of one particle by another corresponds to the dividing or joining together of strings. For example, the gravitational force of the sun on the Earth was pictured in particle theories as being caused by the emission of a gravitation by a particle in the sun and its absorption by a particle in the Earth. In string theory, this process corresponds to an H-shaped tube, or pipe. The two vertical sides of the H correspond to the particles in the sun and the Earth, and the horizontal crossbar corresponds to the gravitation that travels between them. String theory has a curious history. It was originally invented in the late 1960s in an attempt to find a theory to describe the strong force. The idea was that particles like the proton and the neutron could be regarded as waves on a string. The string forces between the particles would correspond to pieces of string that went between other bits of string, as in a spider's web. For this theory to give the observed value of the strong force between particles, the strings had to be like rubber bands with a pull of about 10 tons. In 1974, Joël Cherc from Paris and John Schwartz from the California Institute of Technology published a paper in which they showed that string theory could describe the gravitational force, but only if the tension in the string were very much higher, about 1,000 million tons, one with 39 zeros after it. The predictions of the string theory would be just the same as those of general relativity on normal length scales, but they would differ at very small distances, less than 1,000 millionth of a centimeter. A centimeter divided by 1 with 33 zeros after it. Their work didn't receive much attention, however, because at just about that time, most people abandoned the original string theory of the strong force in favor of the theory based on quarks and gluons, which seemed to fit much better with the observations. Cherc died in tragic circumstances. He suffered from diabetes and went into a coma where no one was around to give him an injection of insulin. So Schwartz was left alone as almost the only supporter of string theory, but now with the much higher proposed value of the string tension. In 1984, interest in strings suddenly revived, apparently for two reasons. One was that people were not really making much progress toward showing that supergravity was finite, or that it could explain the kinds of particles that we observe. The other was the publication of a paper by John Schwartz and Mike Green of Queen Mary College, London, that showed that string theory might be able to explain the existence of particles that have a built-in left-handedness, like some of the particles that we observe. Whatever the reasons, a large number of people soon began to work on a string theory, and a new version was developed of the so-called heterotic string, which seemed as if it might be able to explain the types of particles that we observe. String theories also lead to infinities, but it is thought that they will all cancel out in versions like the heterotic string, though this is not yet known for certain. String theories, however, have a bigger problem. They seem to be consistent only if space-time has either 10 or 26 dimensions instead of the usual 4. Of course, extra space-time dimensions are a commonplace in science fiction. Indeed, they're almost a necessity, since otherwise the fact that relativity implies that one cannot travel faster than light means that it would take far too long to travel between stars and galaxies. The science fiction idea is that maybe one can take a shortcut through a higher dimension. One can picture this in the following way. Imagine that the space we live in has only 2 dimensions and is curved like the surface of an anchor ring or torus. If you were on one side of the inside edge of the ring and you wanted to get to a point on the other side, you would have to go round the inner edge of the ring. However, if you were able to travel in the 3rd dimension, you could cut straight across. Why don't we notice all these extra dimensions if they are really there? Why do we see only 3 space and 1 time dimension? The suggestion is that the other dimensions are curved up into a space of very small size, something like a millionth of an inch. This is so small that we just don't notice it. We see only 1 time and 3 space dimensions, in which space-time is very flat. It is like the surface of an orange. If you look at it close up, it's all curved and wrinkled, but if you look at it from a distance, you don't see the bumps. It appears to be smooth. So it is with space-time. On a very small scale, it is 10-dimensional and highly curved. But on bigger scales, you don't see the curvature of the extra dimensions. If this picture is correct, it spells bad news for would-be space travelers. The extra dimensions would be far too small to allow a spaceship through. However, it raises another major problem. Why should some, but not all, of the dimensions be curled up into a small ball? Presumably, in the very early universe, all the dimensions would have been very curved. Why did 1 time and 3 space dimensions flatten out, while the other dimensions remain tightly curled up? One possible answer is the anthropic principle. 2 space dimensions do not seem to be enough to allow for the development of complicated beings like us. For example, 2-dimensional animals on a 1-dimensional Earth would have to climb over each other in order to get past each other. If a 2-dimensional creature ate something it could not digest completely, it would have to bring up the remains the same way it swallowed them, because if there were a passage right through its body, it would divide the creature into 2 separate halves. Our 2-dimensional being would fall apart. Similarly, it's difficult to see how there could be any circulation of the blood in a 2-dimensional creature. There would also be problems with more than 3 space dimensions. The gravitational force between 2 bodies would decrease more rapidly with distance than it does in 3 dimensions. In 3 dimensions, the gravitational force drops to a quarter if one doubles the distance. In 4 dimensions, it would drop to 1/8, in 5 dimensions to 1/16, and so on. The significance of this is that the orbits of planets like the Earth around the Sun would be unstable. The least disturbance from a circular orbit, such as would be caused by the gravitational attraction of other planets, would result in the Earth spiraling away from or into the Sun. We would either freeze or be burned up. In fact, the same behavior of gravity with distance in more than 3 space dimensions means that the Sun would not be able to exist in a stable state with pressure balancing gravity. It would either fall apart or it would collapse to form a black hole. In either case, it would not be of much use as a source of heat and light for life on Earth. On a smaller scale, the electrical forces that cause the electrons to orbit around the nucleus in an atom would behave in the same way as gravitational forces. Thus, the electrons would either escape from the atom altogether or would spiral into the nucleus. In either case, one could not have atoms as we know them. It seems clear, then, that life, at least as we know it, can exist only in regions of space-time in which 1 time and 3 space dimensions are not curled up small. This would mean that one could appeal to the weak anthropic principle, provided one could show that string theory does at least allow there to be such regions of the universe, and it seems that indeed string theory does. There may well be other regions of the universe, or other universes, whatever that may mean, in which all the dimensions are curled up small, or in which more than 4 dimensions are nearly flat. But there would be no intelligent beings in such regions to observe the different number of effective dimensions. Apart from the question of the number of dimensions that space-time appears to have, string theory still has several other problems that must be solved before it can be acclaimed as the ultimate unified theory of physics. We do not yet know whether all the infinities do cancel each other out, or exactly how to relate the waves on the string to the particular types of particles that we observe. Nevertheless, it is likely that answers to these questions will be found over the next few years, and that by the end of the century we shall know whether string theory is indeed the long-sought-after unified theory of physics. But can there really be such a unified theory? Or are we perhaps just chasing a mirage? There seems to be 3 possibilities. 1, there really is a complete unified theory, which we will someday discover if we are smart enough. 2, there is no ultimate theory of the universe, just an infinite sequence of theories that describe the universe more and more accurately. Or 3, there's no theory of the universe. Events cannot be predicted beyond a certain extent, but occur in a random and arbitrary manner. Some would argue for the 3rd possibility on the grounds that if there were a complete set of laws, that would infringe God's freedom to change his mind and intervene in the world. It's a bit like the old paradox, can God make a stone so heavy that he can't lift it? But the idea that God might want to change his mind is an example of the fallacy pointed out by St. Augustine of imagining God as a being existing in time. Time is a property only of the universe that God created. Presumably, he knew what he intended when he set it up. With the advent of quantum mechanics, we have come to recognize that events cannot be predicted with complete accuracy, but that there is always a degree of uncertainty. If one likes, one could ascribe this randomness to the intervention of God, but it would be a very strange kind of intervention. There's no evidence that it is directed toward any purpose. Indeed, if it were, it would by definition not be random. In modern times, we have effectively removed the 3rd possibility above by redefining the goal of science. Our aim is to formulate a set of laws that enables us to predict events only up to the limit set by the uncertainty principle. The 2nd possibility, that there is an infinite sequence of more and more refined theories, is in agreement with all our experience so far. On many occasions, we have increased the sensitivity of our measurements or made a new class of observations only to discover new phenomena that were not predicted by the existing theory, and to account for these, we have had to develop a more advanced theory. It would therefore not be very surprising if the present generation of grand unified theories was wrong in claiming that nothing essentially new will happen between the electroweak unification energy of about 100 GeV and the grand unification energy of about 1,000 million GeV. We might indeed expect to find several new layers of structure more basic than the quarks and electrons that we now regard as elementary particles. However, it seems that gravity may provide a limit to the sequence of boxes within boxes. If one had a particle with an energy above what is called the Planck energy, 10 million GeV, 1 followed by 19 zeros, its mass would be so concentrated that it would cut itself off from the rest of the universe and form a little black hole. Thus, it does seem that the sequence of more and more refined theories should have some limit as we go higher and higher energies, so that there should be some ultimate theory of the universe. Of course, the Planck energy is a very long way from the energies of around 100 GeV, which are the most that we can produce in the laboratory at the present time. We shall not bridge that gap with particle accelerators in the foreseeable future. The very early stages of the universe, however, are an arena where such energies must have occurred. I think that there is a good chance that the study of the early universe and the requirements of mathematical consistency will lead us to a complete unified theory within the lifetime of some of us who are around today, always presuming we don't blow ourselves up first. What would it mean if we actually did discover the ultimate theory of the universe? As was explained in Chapter 1, we could never be quite sure that we had indeed found the correct theory, since theories can't be proved. But if the theory was mathematically consistent and always gave predictions that agreed with observations, we could be reasonably confident that it was the right one. It would bring to an end a long and glorious chapter in the history of humanity's intellectual struggle to understand the universe. But it would also revolutionize the ordinary person's understanding of the laws that govern the universe. In Newton's time, it was possible for an educated person to have a grasp of the whole of human knowledge, at least in outline. But since then, the pace of the development of science has made this impossible, because theories are always being changed to account for new observations. They are never properly digested or simplified so that ordinary people can understand them. You have to be a specialist, and even then, you can only hope to have a proper grasp of a small proportion of the scientific theories. Further, the rate of progress is so rapid that what one learns at school or university is always a bit out of date. Only a few people can keep up with the rapidly advancing frontier of knowledge, and they have to devote their whole time to it and specialize in a small area. The rest of the population has little idea of the advances that are being made or the excitement that they are generating. 70 years ago, if Eddington is to be believed, only 2 people understood the general theory of relativity. Nowadays, tens of thousands of university graduates do, and many millions of people are at least familiar with the idea. If a complete unified theory was discovered, it would only be a matter of time before it was digested and simplified in the same way and taught in schools, at least in outline. We would then all be able to have some understanding of the laws that govern the universe and are responsible for our existence. Even if we do discover a complete unified theory, it would not mean that we would be able to predict events in general for 2 reasons. The first is the limitation that the uncertainty principle of quantum mechanics sets on our powers of prediction. There's nothing we can do to get around that. In practice, however, this first limitation is less restrictive than the second one. It arises from the fact that we could not solve the equations of the theory exactly, except in very simple situations. We cannot even solve exactly for the motion of 3 bodies in Newton's theory of gravity, and the difficulty increases with the number of bodies and the complexity of the theory. We already know the laws that govern the behavior of matter under all but the most extreme conditions. In particular, we know the basic laws that underlie all of chemistry and biology, yet we have certainly not reduced these subjects to the status of solved problems. We have, as yet, had little success in predicting human behavior from mathematical equations. So even if we do find a complete set of basic laws, there will still be, in the years ahead, the intellectually challenging task of developing better approximation methods so that we can make useful predictions of the probable outcomes in complicated and realistic situations. A complete, consistent, unified theory is only the first step. Our goal is a complete understanding of the events around us and of our own existence. Chapter 11. Conclusion. We find ourselves in a bewildering world. We want to make sense of what we see around us and to ask, what is the nature of the universe? What is our place in it? And where did it and we come from? Why is it the way it is? To try to answer these questions, we adopt some world picture. Just as an infinite tower of tortoises supporting the flat Earth is such a picture, so is the theory of superstrings. Both are theories of the universe, though the latter is much more mathematical and precise than the former. Both theories lack observational evidence. No one has ever seen a giant tortoise with the Earth on its back, but then no one has seen a superstring either. However, the tortoise theory fails to be a good scientific theory because it predicts that people should be able to fall off the edge of the world. This has not been found to agree with experience unless that turns out to be the explanation for the people who are supposed to have disappeared in the Bermuda Triangle. The earliest theoretical attempts to describe and explain the universe involved the idea that humans and natural phenomena were controlled by spirits with human emotions who acted in a very human-like and unpredictable manner. These spirits inhabited natural objects like rivers and mountains, including celestial bodies like the sun and the moon. They had to be placated and their favors sought in order to ensure the fertility of the soil and the rotation of the seasons. Gradually, however, it must have been noticed that there were certain regularities. The sun always rose in the east and set in the west, whether or not a sacrifice had been made to the sun god. Further, the sun, the moon, and the planets followed precise paths across the sky that could be predicted in advance with considerable accuracy. The sun and the moon might still be gods, but they were gods who obeyed strict laws, apparently without any exceptions, if one discounts stories like that of the sun stopping for Joshua. At first, these regularities and laws were obvious only in astronomy and a few other situations. However, as civilization developed, and particularly in the last 300 years, more and more regularities and laws were discovered. The success of these laws led Laplace at the beginning of the 19th century to postulate scientific determinism. That is, he suggested that there would be a set of laws that would determine the evolution of the universe precisely, given its configuration at one time. Laplace's determinism was incomplete in two ways. It did not say how the laws should be chosen, and it did not specify the initial configuration of the universe. These were left to God. God would choose how the universe began and what laws it obeyed, but he would not intervene in the universe once it had started. In effect, God was confined to the areas that 19th century science did not understand. We now know that Laplace's hopes of determinism cannot be realized, at least in the terms he had in mind. The uncertainty principle of quantum mechanics implies that certain pairs of quantities, such as the position and velocity of a particle, cannot both be predicted with complete accuracy. Quantum mechanics deals with this situation via a class of quantum theories in which particles don't have well-defined positions and velocities, but are presented by a wave. These quantum theories are deterministic in the sense that they give laws for the evolution of the wave with time. Thus, if one knows the wave at one time, one can calculate it at any other time. The unpredictable random element comes in only when we try to interpret the wave in terms of the positions and velocities of particles. But maybe that is our mistake. Maybe there are no particle positions and velocities, but only waves. It is just that we try to fit the waves to our preconceived ideas of positions and velocities. The resulting mismatch is the cause of the apparent unpredictability. In effect, we have redefined the task of science to be the discovery of laws that will enable us to predict events up to the limits set by the uncertainty principle. The question remains, however, how or why were the laws and the initial state of the universe chosen? In this book, I've given special prominence to the laws that govern gravity, because it is gravity that shapes the large-scale structure of the universe, even though it is the weakest of the four categories of force. The laws of gravity were incompatible with the view held until quite recently that the universe is unchanging in time. The fact that gravity is always attractive implies that the universe must be either expanding or contracting. According to the general theory of relativity, there must have been a state of infinite density in the past, the Big Bang, which would have been an effective beginning of time. Similarly, if the whole universe recollapsed, there must be another state of infinite density in the future, the Big Crunch, which would be an end of time. Even if the whole universe did not recollapse, there would be singularities in any localized regions that collapse to form black holes. These singularities would be an end of time for anyone who fell into the black hole. At the Big Bang and other singularities, all the laws would have broken down, so God would still have had complete freedom to choose what happened and how the universe began. When we combine quantum mechanics with general relativity, there seems to be a new possibility that did not arise before, that space and time together might form a finite four-dimensional space without singularities or boundaries, like the surface of the Earth, but with more dimensions. It seems that this idea could explain many of the observed features of the universe, such as its large-scale uniformity and also the smaller-scale departures from homogeneity like galaxies, stars, and even human beings. It could even account for the arrow of time that we observe. But if the universe is completely self-contained with no singularities or boundaries and completely described by a unified theory, that has profound implications for the role of God as creator. Einstein once asked the question, how much choice did God have in constructing the universe? If the no-boundary proposal is correct, he had no freedom at all to choose initial conditions. He would, of course, still have had the freedom to choose the laws that the universe obeyed. This, however, may not really have been all that much of a choice. There may well be only one or a small number of complete unified theories, such as the heterotic string theory, that are self-consistent and allow the existence of structures as complicated as human beings who can investigate the laws of the universe and ask about the nature of God. Even if there is only one possible unified theory, it is just a set of rules and equations. What is it that breathes fire into the equation and makes a universe for them to describe? The usual approach of science, of constructing a mathematical model, cannot answer the questions of why there should be a universe for the model to describe. Why does the universe go to all the bother of existing? Is the unified theory so compelling that it brings about its own existence, or does it need a creator? And if so, does he have any other effect on the universe? And who created him? Up to now, most scientists have been too occupied with the development of new theories that describe what the universe is to ask the question, why? On the other hand, the people whose business is to ask why, the philosophers, have not been able to keep up with the advance of scientific theories. In the 18th century, philosophers considered the whole of human knowledge, including science, to be their field and discussed questions such as, did the universe have a beginning? However, in the 19th and 20th centuries, science became too technical and mathematical for the philosophers or anyone else except a few specialists. Philosophers reduced the scope of their inquiries so much that Wittgenstein, the most famous philosopher of this century, said, the sole remaining task for philosophy is the analysis of language. What a come down from the great tradition of philosophy from Aristotle to Kant. However, if we do discover a complete theory, it should in time be understandable in broad principle by everyone, not just a few scientists. Then we shall all, philosophers, scientists, and just ordinary people, be able to take a part in the discussion of the question of why it is that we and the universe exist. If we find the answer to that, it would be the ultimate triumph of human reason, for then we would know the mind of God. Albert Einstein. Einstein's connection with the politics of the nuclear bomb is well known. He signed the famous letter to President Franklin Roosevelt that persuaded the United States to take the idea seriously, and he engaged in post-war efforts to prevent nuclear war. But these were not just the isolated actions of a scientist dragged into the world of politics. Einstein's life was, in fact, to use his own words, divided between politics and equations. Einstein's earliest political activity came during the First World War, when he was a professor in Berlin. Sickened by what he saw as the waste of human lives, he became involved in anti-war demonstrations. His advocacy of civil disobedience and public encouragement of people to refuse conscription did little to endear him to his colleagues. Then, following the war, he directed his efforts toward reconciliation and improving international relations. This, too, did not make him popular, and soon his politics were making it difficult for him to visit the United States, even to give lectures. Einstein's second great cause was Zionism. Although he was Jewish by descent, Einstein rejected the biblical idea of God. However, a growing awareness of anti-Semitism, both before and during the First World War, led him gradually to identify with the Jewish community, and later to become an outspoken supporter of Zionism. Once more, unpopularity did not stop him from speaking his mind. His theories came under attack. An anti-Einstein organization was even set up. One man was convicted of inciting others to murder Einstein and fined a mere $6. But Einstein was phlegmatic. When a book was published entitled 100 Authors Against Einstein, he retorted, "If I were wrong, then one would have been enough." In 1933, Hitler came to power. Einstein was in America and declared he would not return to Germany. Then, while Nazi militia raided his house, confiscated his bank account, a Berlin newspaper displayed the headline, "Good news from Einstein. He's not coming back." In the face of the Nazi threat, Einstein renounced pacifism and eventually, fearing that German scientists would build a nuclear bomb, proposed that the United States should develop its own. But even before the first atomic bomb had been detonated, he was publicly warning of the dangers of nuclear war and proposing international control of nuclear weaponry. Throughout his life, Einstein's efforts towards peace probably achieved little that would last, and certainly won him few friends. His vocal support of the Zionist cause, however, was duly recognized in 1952 when he was offered the presidency of Israel. He declined, saying he thought he was too naive in politics, but perhaps his real reason was different. To quote him again, "Equations are more important to me because politics is for the present, but an equation is something for eternity." Galileo, perhaps more than any other single person, was responsible for the birth of modern science. His renowned conflict with the Catholic Church was central to his philosophy, for Galileo was one of the first to argue that man could hope to understand how the world works, and moreover, that we could do this by observing the real world. Galileo had believed Copernican theory, that the planets orbited the sun, since early on, but it was only when he found the evidence needed to support the idea that he started to publicly support it. He wrote about Copernicus's theory in Italian, not the usual academic Latin, and soon his views became widely supported outside the universities. This annoyed the Aristotelian professors, who united against him, seeking to persuade the Catholic Church to ban Copernicanism. Galileo, worried by this, traveled to Rome to speak to the ecclesiastical authorities. He argued that the Bible was not intended to tell us anything about scientific theories, and that it was usual to assume that where the Bible conflicted with common sense, it was being allegorical. But the Church was afraid of a scandal that might undermine its fight against Protestantism, and so took repressive measures. It declared Copernicanism false and erroneous in 1616, and commanded Galileo never again to, quote, defend or hold the doctrine. Galileo acquiesced. In 1623, a longtime friend of Galileo's became the Pope. Immediately, Galileo tried to get the 1616 decree revoked. He failed, but he did manage to get permission to write a book discussing both Aristotelian and Copernican theories on two conditions. He would not take sides and would come to the conclusion that man could, in any case, not determine how the world worked because God could bring about the same effects in ways unimagined by man, who could not place restrictions on God's omnipotence. The book, Dialogue Concerning the Two Chief World Systems, was completed and published in 1632 with the full backing of the censors, and was immediately greeted throughout Europe as a literary and philosophical masterpiece. Soon the Pope, realizing that people were seeing the book as a convincing argument in favor of Copernicanism, regretted having allowed its publication. The Pope argued that although the book had the official blessing of the censors, Galileo had nevertheless contravened the 1616 decree. He brought Galileo before the Inquisition, who sentenced him to house arrest for life and commanded him to publicly renounce Copernicanism. For a second time, Galileo acquiesced. Galileo remained a faithful Catholic, but his belief in the independence of science had not been crushed. 4 years before his death in 1642, while he was still under house arrest, the manuscript of his second major book was smuggled to a publisher in Holland. It was this work, referred to as Two New Sciences, even more than his support for Copernicus, that was to be the genius of modern physics. Isaac Newton. Isaac Newton was not a pleasant man. His relations with other academics was notorious, with most of his later life spent embroiled in heated disputes. Following publication of Principia Mathematica, surely the most influential book ever written in physics, Newton had risen rapidly into public prominence. He was appointed president of the Royal Society and became the first scientist ever to be knighted. Newton soon clashed with the Astronomer Royal, John Flamsteed, who had earlier provided Newton with much-needed data for Principia, but was now withholding information that Newton wanted. Newton would not take no for an answer. He had himself appointed to the governing body of the Royal Observatory and then tried to force immediate publication of the data. Eventually, he arranged for Flamsteed's work to be seized and prepared for publication by Flamsteed's mortal enemy, Edmund Halley. But Flamsteed took the case to court and, in the nick of time, won a court order preventing distribution of the stolen work. Newton was incensed and sought his revenge by systematically deleting all references to Flamsteed in later editions of Principia. A more serious dispute arose with the German philosopher Gottfried Leibniz. Both Leibniz and Newton had independently developed a branch of mathematics called calculus, which underlies most of modern physics. Although we know now that Newton discovered calculus years before Leibniz, he published his work much later. A major row ensued over who had been first, with scientists vigorously defending both contenders. It is remarkable, however, that most of the articles appearing in defense of Newton were originally written by his own hand and only published in the name of friends. As the row grew, Leibniz made the mistake of appealing to the Royal Society to resolve the dispute. Newton, as president, appointed an impartial committee to investigate, coincidentally consisting entirely of Newton's friends. But that was not all. Newton then wrote the committee's report himself and had the Royal Society publish it, officially accusing Leibniz of plagiarism. Still unsatisfied, he then wrote an anonymous review of the report in the Royal Society's own periodical. Following the death of Leibniz, Newton is reported to have declared that he had taken great satisfaction in breaking Leibniz's heart. During the period of these two disputes, Newton had already left Cambridge and academia. He had been active in anti-Catholic politics at Cambridge and later in Parliament, and was rewarded eventually with the lucrative post of Warden of the Royal Mint. Here he used his talents for deviousness and vitriol in a more socially acceptable way, successfully conducting a major campaign against counterfeiting, even sending several men to their death on the gallows. And that's a brief history of time, from the Big Bang to black holes by Stephen W. Hawking, with an introduction by Carl Sagan, read by Michael Jackson.
Okay, everyone. Looks like we made it through that. That was a lot to take in. Right, that was definitely a lot of knowledge to take in. Right, guys, it went from everything from colors to time to stars to God, to religion, to different scientists, to the 60s, to Yale, to all that, to everything. Talked about a brief history of time. Now that was all incredible. All right, I'm gonna listen to all of this footage, and I'm gonna take notes. I'm glad I did this because I really wanted to get this audiobook on my channel, and now it's finally done. I'm sorry if I was lazy at times, but you know, you do get lazy, you just take in all of this knowledge, and then it's like, okay, because you're trying to take it in, especially when you're a newbie and you're listening to an audiobook. You guys kind of know what I mean. You haven't read a book in a while. I have about 30 books. Most of them are fiction fantasy, like Harry Potter and Game of Thrones and Lord of the Rings, but I have 30 books that I have to read that I'm gonna read within half a year, pretty much. So, but that's a goal. That's a goal. It's not something that I'm saying that I'm gonna do for sure. I know I'm gonna do it, but it's a goal, right? The goal is to be educated and to cut back on the marijuana. But other than that, just having fun and casually listening to an audiobook written by the greatest scientist who ever exists, with an introduction by one of the greatest cosmologists to ever exist. You know, it's really a treat to just be able to listen to that in itself. You know, I can't even begin to tell you guys how grateful I am that I lived in a world that Stephen Hawking lived in. You know, I can't even begin to tell you, I can't believe I live in a world where a super genius man changed the world with all of these immaculate discoveries. The guy is incredible. God bless him. And he had that ailment, and he still pulled through. He didn't let it bring him down. You know, that's motivation. That's motivational for all the ages. Do you guys know what I mean? That's forever. That's forever remembered as someone super interesting, super useful to society. So tonight I'm going to actually, before I go any further with this, I have to tell you I'm going to take notes on all of the footage of the audiobook, and I'm gonna take it in. I'm gonna take it in. I'm gonna clip it. Yeah. You know, so I wanted to let everyone know I'm thankful. I'm thinking about making this channel into two different things. One with the single playlist, two playlists, one for shorts for gaming and one for you know, I'll figure it out. But I have a documentary that we're gonna watch, and I'm gonna get that ready now. So peace out, everyone.